Hello, everyone, and thank you so much for joining our webinar today. I would like to welcome you all to our session on code standards and regulations and insurance gap analysis for hydrogen value chain development in Alberta. My name is Vanessa Foran, and I'm the Responsible Care Program Officer at the Chemistry Industry Association of Canada. Before we get started, I would like to begin by acknowledging that while we are meeting on a virtual platform, the CIAC's office is located on the traditional and unceded territory of the Algonquin Anishinaabe people. They have occupied and have been the guardians of this land since time immemorial. Today, this place is still the home of many Indigenous people, and we are grateful to have the opportunity to be present in this territory. We also acknowledge and appreciate that there are a number of participants in today's webinar coming from other traditional Indigenous lands across North America. For those of you just joining us, welcome. A recorded version of this webinar will be available on the CIAC's website. We would love to hear from you, and there will be an opportunity for questions after each of our panelist presentations. Please submit your questions in the Q&A chat below. I would now like to introduce our panelists. Today we have joining us from the University of Alberta, Dr. Lianne Lefsrud, the Risk, Innovation, and Sustainability Chair and Associate Professor and Director of Outreach, Chemical and Materials Engineering. We also have joining us Dr. Fereshteh Sattari, Research Director at the Lynch School of Engineering, Safety, and Risk Management. And we also have joining us Anirudha Joshi, a Graduate Research Assistant at the Faculty of Engineering at the University of Alberta. So thank you so much for joining us today, and I'll hand it over to our panelists.
Yeah. Thank you, Vanessa. If you could share the slides, please, that would be wonderful. Thank you. Thank you, everyone, for making time today to talk about how we can use quantitative risk assessment to look at a novel, at least to Alberta anyway, a novel technology with regards to hydrogen in the value chain and various applications in it. So I just also would like to acknowledge the fact that we also have Dr. Adnan Khan, who is a principal investigator in this, and also unveil, who is a representative from Strathcona County, who's contributed to this work. Additionally, we couldn't do this without the funding of Alberta Innovates, the Transition Accelerator, and then in kind from Strathcona County and Sturgeon County. So next slide, please, Vanessa. So the motivation for this is Canada is the 11th largest contributor to greenhouse gas emissions, and 9% of Canada's emissions are from heavy-duty transportation. So if we're going to reduce our emissions, we have to really think about to transitioning to zero-emission energy carriers like hydrogen. And we're really, the push is on in Alberta, especially to look at high priority and use of hydrogen as a fuel. And unfortunately, however, regulation does not exist. So what we're doing is looking at how we can improve investment and the development of hydrogen by identifying and addressing those regulatory gaps to be able to minimize uncertainty among stakeholder groups. Next slide, please. So hydrogen is fantastic, as we all know. It's a clean fuel with zero greenhouse gas emissions, an excellent energy carrier, diverse domestic sources, economically competitive, and has a faster refueling time than battery vehicles, and also non-toxic. So we have certain, like railroads, for example, or CP, KC are moving to hydrogen locomotives, for example, as opposed to battery locomotives, just because of the faster refueling time, as an example. Next slide, please. However, it's also highly hazardous. It's a tiny molecule, so it's always leaking, as you can imagine. Very low viscosity. It diffuses quite quickly, unfortunately, and has a very low ignition energy, very broad flammability, explosivity range, and is colorless, odorless, and tasteless. So although it's a fantastic energy carrier, it also has very hazardous characteristics. As a result of this, the figure 4 on the right-hand side, you can see there's been a number of hydrogen incidents in the EU since 1985, primarily explosion, 48%, fire, 24%, release, 11%, burst of a tank, 3%, and then also pipe rupture and just regular fires. So it's highly hazardous, and as a result has led to a series of incidents. Next slide, please. So what we'd like to talk about today is our approach generally which is to look at the CSA Standard Council of Canada, the identified gaps, but how can we prioritize those gaps? And it's primarily to then look at the safety, process safety issues with regards to hydrogen, and using a quantitative risk assessment for specific use case scenarios to determine where those gaps exist, compare against municipalities' codes and standards versus other jurisdictions, California, Japan, other places where they have been using hydrogen for a number of years in a way that is safe and effective, so that we can enshrine a safety-first approach in Alberta. We'll talk about hydrogen refueling station as our first use case example, and we'll talk about some next steps. Next slide, please. Okay, so what we did is basically follow the molecule to analyze these use cases. So look very much at the full hydrogen value chain. So in this Alberta Innovates funded research, we have basically 5 milestones or 5 sub-projects that we're looking at. The first is hydrogen vehicle fueling and servicing, in which Anirudha will show our approach. Number 2 is transportation, and that's primarily on roads and pipelines, which is also the third milestone. We're also going to look at microgeneration, and then lastly, end use in various residential, commercial, heavy equipment, and then also power generation. Okay, next slide, please. Now I'll pass it over to Dr. Fereshteh Sattari, and she'll talk about our first use case in hydrogen refueling stations.
Yes. So thank you, Dr. Lianne. First, I want to thank everybody for taking the time and join us. Now I'm talking about the motivation behind this research. To support the transition to hydrogen-powered heavy-duty vehicles, the government of Alberta has called for expressions of interest from stakeholders and local parties willing to own and operate hydrogen refueling stations in the province. The expected station capacity is around 2 tons of hydrogen per day, primarily focusing on serving heavy-duty vehicles. However, these stations may also have future provisions for fueling light-duty hydrogen vehicles. To facilitate the deployment of hydrogen-powered heavy-duty vehicles, it is crucial to establish a robust hydrogen refueling network across the province. Next slide, please. While deploying hydrogen refueling stations offers environmental benefits, several obstacles or challenges impede their facilitation in Alberta. These obstacles stem from various safety concerns regarding using hydrogen as a fuel, gaps in local zoning laws, Canadian codes and standards, and the process for permitting and approval considering these safety concerns. Additionally, most quantitative risk assessment performed for hydrogen refueling stations assume a uniform leak size distribution throughout the facility, which can lead to an over or underestimation of required separation distances. Next slide, please. Now, let's talk about the main objectives of this research. The primary objective of this study was to perform a quantitative risk assessment or QRA of a pseudo-hydrogen refueling station located in Edmonton, Alberta, and identify the potential risk associated with such a facility. Furthermore, the study aimed to estimate appropriate separation distances based on the leak size derived from different areas within the pseudo-refueling station, considering their respective pipe flow rates, And finally, the study tried to come up with the applicable codes, standard, and provincial zoning laws related to hydrogen refueling stations and identify any gaps or shortcomings that must be addressed. Next slide, please. Let's talk about this pseudo hydrogen refueling station, which we call it PHRS. For this specific study, a pseudo hydrogen refueling station was modeled and derived into three main areas based on their pipe flow areas: the tube trailer area, the hydrogen system area, and the dispenser area, as you can see in this figure. Two operating scenarios were considered for the PHRS model. Scenario 1 involved refueling heavy-duty vehicles at a dispensing pressure of 350 bar, and scenario 2 considered refueling light-duty vehicles at a higher dispensing pressure of 700 bar. Next slide, please. Now let's talk about the facility description. This slide provides a detailed description of the equipment, pressures, and hydrogen inventories considered in these two operating scenarios for the modeled pseudo HRS. In scenario 1, as you can see, for refueling heavy-duty vehicles at 350 bar, the facility included two tube trailer with a pressure of 500 bar and an inventory of 1,000 kg each, a compressor operating at 520 bar, a medium pressure storage tank at 520 bar with a 500 kg inventory and a dispenser at 350 bar. In scenario 2, for refueling light-duty vehicles at 700 bar, the facility had the same two tube trailers with a pressure of 500 bar and an inventory of 1,000 kg each. However, the compressor operated at a higher pressure of 900 bar, and there was a high pressure storage tank at 900 bar with a 1,000 kg inventory. The dispenser in this scenario was rated at for 700 bar. Figure 6 on the right side shows the location chosen for the modeling of the PHRS, which is a currently operational diesel truck stop on Pembina Road in Sherwood Park, situated in Edmonton's east-west high traffic economic corridor. And figure 7 illustrates the layout of the PHRS facility, which was developed to comply with the NFPA 2 code for performing the quantitative risk assessment. Next slide, please. Now let's talk about the methodology that we took for this research. The quantitative risk assessment methodology followed in this study was based on the conventional approach outlined in the Purple Book, integrated with the risk-informed method of evaluating separation distances as described in the work done by Sandia National Lab and NFPA. For each area in PHRS, namely the tube trailer area, the hydrogen system area, and dispenser area, individual equipment failure frequencies were calculated using Hiram tool. A bow tie analysis was then conducted to evaluate the frequency of leak occurrence, followed by an assessment for the potential consequences of these leaks. A risk matrix following the guidelines provided by the Center for Chemical Process Safety, or CCPS, was developed to assess the severity of the consequences. These matrix categorized a risk as intolerable, not desirable, conditionally acceptable with controls, or tolerable based on the frequency and consequences severity. Individual risk levels and separation distances were evaluated for the 350 bar and 750 bar scenarios. Additionally, the impact of relevant safety barriers on the overall risk at the PHRS was calculated, considering the intolerable and undesirable risk levels. Now I want to invite Anirudha to present some of the results. Next
Thank you so
slide,
much.
please.
Thank you so much, Dr. Sattari and Dr. Lianne, for that introduction to the project and the work we have done. So now coming to the very first risk assessment tool we have used in this study was the bow ties we have developed. So there was one main event that we considered, that is a leak occurring in the PHRS. And possibly there were three different areas from where the leak could occur, as was described by Dr. Sattari. We have the tube trailer area, we have the hydrogen system area, and we have the dispenser area. So in this case, as we can see here in the diagram, the top event is the hydrogen leak. And the causes can be either leak from the tube trailer area, which is indicated by P1. The second is either from the leak from the hydrogen system area, which is indicated by P2. And the third is leak from the dispenser area, as is indicated with P3. Now, following these P1, P2, and P3, there can be several causes that can lead to leak in these particular areas and ultimately leading to the top event. So we categorized each leak based upon the number of equipments that are installed, or the type of equipments and components that are installed in each area. For example, in P1, P1.1 to P1.6 talks about the components that are installed in P1, and leak from any of these components can lead to leakage from that particular area, and ultimately can lead us to the top event. So as we can see, we have used the OR gate. So either leakage from, let's say, the cylinder present in the P1 area, or let's say a valve present, or the pipeline that is associated in that area. Any of this can lead us to the top event of the primary leakage of hydrogen in the PHRS. So the left-hand side talks about the fault tree analysis that was developed in the study. And the right-hand side of the top event talks about the event tree analysis that was developed based upon the ignition conditions that occur. So for example, if there's an immediate ignition after a hydrogen leak has occurred, the consequence can be E1, which is the jet fire in this case. Similarly, if there's a delayed ignition in the process, then the consequence can be a flash fire. And in any situation, if there's no ignition at all, the consequence can be a safe dispersion. That means the hydrogen has diluted and there's no probability of ignition in such events. Next slide, please. So based upon these bow tie, we calculated what can be the frequency of occurrence of hydrogen leak in such situations. And as Dr. Sattari said, we were looking forward to take about the assumption of uniform leak sizing throughout the refilling station. So we looked at different leak sizes at different areas based upon their pipe flow areas associated to each area. Now, as we can see, we have 0.1% leak size, 1%, 10%, and 100%. Now, these are relative to the pipe flow area associated to each component of the refilling station. So based upon these leak sizes, we evaluated what is the frequency of that top event occurring, what is the frequency of consequence E1, that is jet fire, consequence E2, flash fire, and consequence E3, that is safe dispersion. And based upon this, we could see that the annual frequency of occurrence for a leak size of 1% and 10% had a relatively smaller difference of just 0.02. And now this is very considerable, because if for example, if we consider that there's a 1% leak size, which is a smaller leak size as compared to 10 and 100%, then we'd be underestimating the harm that can be caused because of a 10% leak size. So for example, 1% leak size is somewhere around 0.62 mm, whereas a 10% leak size is somewhere around 3 mm. So in this case, of course, the 3 mm leak hole can generate higher distances, higher harm distances as compared to the smaller size. So therefore, in order to not undermine and to have a conservative approach to look at the separation distances, we considered a 10% leak scenario as a potential leak size for the entire station. Now, again, this 10% scenario would be different for the tube trailer area, for the hydrogen system area, as well as for the dispenser area. And this 10% scenario was the basis to calculate the consequences, or in other words, the harm distances. Next slide, please. So based upon the frequencies we adhered, we developed a risk matrix with the guidelines given by CCPS for hazard evaluation procedures. And in this, we can see based upon the frequency of occurrence, each event or each consequence has been categorized either as intolerable, not desirable, conditionally acceptable with certain engineering and administrative controls in place, and the last is considered to be tolerable. So based upon the bow tie and the fault tree and the event tree developed, we could see that the jet fire event that occurs generally whenever we have an immediate ignition was intolerable, followed by the flash fire event, which generally occurs when there's delayed ignition, was not desirable, and safe dispersion, of course, in certain cases wherein we have acceptable controls, was considered to be conditionally acceptable, making a note that we have all of those, let's say, ventilation system or gas detection system in place. Next slide, please. So based upon this risk matrix and the risks, the different leak sizes evaluated, we had to set certain harm and risk criteria so we could estimate the distances based upon that threshold levels. So in this case, particularly whenever we have ignition, we look at thermal radiation levels developed. So the primary one is 1.6 kilowatt per meter square. And in this thermal radiation, there's generally no harm even for longer exposures. But as we go to the 4.7 kilowatt per meter square thermal radiation level, so if any individual is exposed for near about to 20 seconds at this thermal radiation level, that human can experience first degree burns. Similarly, if we go for a higher radiation, that is 25 kilowatt per meter square, the human can experience significant injury in just 10 seconds and even 100% lethality in a minute. So looking at this thermal levels, we concluded that 4.7 kilowatt per meter square is that particular threshold that we need to look at, because that provides us a 20-second escape time as well. So any human beyond this will be in the thermal radiation range from 1.6 to 4.7, which is considered to be less harmful or at a stage no harmful. So therefore 4.7 kilowatt per meter square was our ideal threshold value to consider as the criteria. And apart from that, not just the thermal radiation level, but let's say if there's no ignition, then the hydrogen will keep accumulating and the concentration of hydrogen can reach about the 4 volume %, which is the lower flammability limit of hydrogen. So even in this case, hydrogen, if an ignition source is present, can ignite and can result in flash fire due to delayed ignition. So we set these two boundary conditions in order to determine at what distances humans are going to be safe. So the first is 4.7 kilowatt per meter square, and the second is the LFL concentration. Whichever generated the higher results or higher distances, we considered that as the separation distances. And this was in line with the methodology that is used by National Fire Protection Association in their published article, especially for hydrogen in NFPA 2. Next slide, please. Okay, so now we have the frequency part understood already. Now let's talk about the consequences that these leaks have. So as Dr. Sattari described, we have two scenarios. Scenario 1 talks about the 350 bar refueling station wherein we are refueling heavy duty vehicles, and scenario 2 that is 700 bar wherein we are refueling the light duty vehicles. So as we see, based upon the boundary conditions we set, in the first scenario for jet fire, the dispenser area has the highest harm distance near about to 30 meters. Then if we look at the LFL cloud, that is the concentration, 4 volume % concentration of hydrogen reaching, and that is highest for the tube trailer area. Now here, the particular reason for this is higher pipe flow area as well as higher inventory of hydrogen present in the tube trailer area. Now see, the assumption of having a uniform leak size would have probably gotten us some different results. Either the hydrogen storage area would have the higher distances, or maybe the dispenser island would have had the higher distances. But in this case, since we are looking at the relative pipe flow area, the tube trailer area causes higher distances in this scenario. So it was important for us to differentiate these areas based upon what pipe system or what pipe sizing they have. Secondly, we talk about the second scenario. As we can see, there's a drastic rise in the dispenser area, especially for the jet fire scenario, wherein the thermal radiation level can reach up to 40 meters from the risk source. So in this case, the primary reason for this is whenever we are refueling hydrogen at 700 bars, since we are going to compress it to 700 bars, which is notably a higher pressure, we need to cool it down to minus 40 degrees Celsius. Now, if there's a leak at that point, let's say in the dispenser area where you're refilling your vehicle and there's a drive off or there's a leak at that particular point, and if there's a release of hydrogen, the colder gas will tend to move towards the ground because it has a higher density. And after some time, as the hydrogen gas warms up, it has already traveled extended distance. So that was a particular reason we have a drastic upgrade here to 40 meters from 30 meters in the previous scenario. Next slide, please. So now, in order to quantify and put a number to the risk based upon the frequency we have and the consequences we have calculated, we estimated the individual risk for both the scenarios. And this is crucial to understand that what human being in what position or in what location in this particular hydrogen refilling station is exposed to what levels of risks. That gives us an idea whether they are in the tolerable region or somewhere in a region which is highly risky or can be called as a high risk zone. So in this case, the workers engaged in the unloading region, let's say if there's a tube trailer that has arrived and there are workers who are going to unload that hydrogen in the hydrogen system area, those people as well as the maintenance operators which are operating in the hydrogen system area are all exposed to a tolerable individual risk of 10 to the power minus 5 fatalities per year. And the humans which are in proximity to the hydrogen system area, which are within the retailer shop that is present in the particular refilling station, and the ones who are near the dispenser area are exposed to an individual risk of 10 to the power minus 6 fatalities per year. Now, there's a particular difference in scenario 1 and scenario 2. If you can see in the right side figure, there's the contours are concentrating more towards the dispenser area. Now, the particular reason for this is the higher harm distances that are getting caused in the dispenser area. As we saw in the previous slide, the distances went up to 40 meters, which is the highest noted up till now for this particular region. And therefore, we can see the risk contour there is highly concentrated and the value increases from 10 to the power minus 6 to 10 to the power minus 5. So that is where the precautions needs to be made. Next slide, please. Okay. So based upon the separation distance criteria set and as well as the boundary conditions we have in this, the separation distances were estimated as we had discussed previously, whichever was higher was considered. So as we can see, the tube trailer area in both the scenarios, the recommended separation distance is near about to 19 meters. So humans beyond this distance are exposed to risks that are tolerable, and people will have sufficient time to escape, so to have absolutely no harm in any hazardous scenario. Similarly, in the first scenario, the hydrogen system area, the recommended separation distance is near about to 12 meters. And for the dispenser area, the recommended distance is near about to 28 meters. Now, again, this is dependent upon either the thermal radiation level is higher or the LFL zone reaches a higher distance, whichever is higher has been selected. In the second scenario, the tube trailer area remains the same, 19 meters. For hydrogen system area, of course, we have increasing pressures. We have compressors operating at 900 bars, and the higher pressure storage tank is maintained at that higher bar pressure. So therefore, the distance has slightly increased from 12 meters in the first scenario to 16 meters in the second scenario. And the dispenser area in the second scenario experiences the highest or meets the highest separation distance, that is 39.1 meters in this scenario. Next slide, please. So now, in order to mitigate or reduce these risks, we looked at certain safety barriers, and based upon their probabilities of failure on demand, based upon the historical evidences we have and the literatures available, we chose 3 relevant safety barriers. The first was gas detection system, the automatic shutdown system, and the emergency ventilation. So the process behind this is basically, if there's a leak in any area, the gas detection system is supposed to detect it immediately. Based upon the detection, it should trigger the automatic shutdown system. The entire electric supply to the HSA, as well as the inventory that is getting supplied to the dispenser area and the HSA, should stop immediately. And there should be certain provision for that particular hydrogen if it has leaked already. And if there's certain level of accumulation, it should be urgently ventilated. So there's a provision for emergency ventilation. So based upon whether these 3 safety barriers work properly, or they are successful, or they fail to work, we have the conditions for ignition. Let's say if there's a detection system, there's an automatic shutdown system, and there's an emergency ventilation, all of them fail at the same time. What would be the consequence? What would be the frequency of consequence we'll be looking at? Secondly, if one of them fails or one of them is successful, what are the frequencies of consequences we are looking at? So this entire inventory was based upon the probability of failure on demand and the probability of immediate and delayed ignition for hydrogen. So based upon this, we can see there are different consequences, whether based upon if, let's say, the gas detection system is successful, the automatic shutdown system is successful, as well as the emergency ventilation is successful, then ultimately we won't have any ignition event, and the final event would be safe dispersion. But any of them fails, and let's say we have immediate ignition, the consequence still would be jet fire. And similarly, if it is delayed, we have a flash fire. Next slide, please. So to study these impact, we tried to quantify. And so as we consider the 10% leak size scenario in our refilling station, as we can see, the frequency of occurrence without the safety barriers was in the range of 10 to the power minus 4 per year. And now after using these safety barriers, considering the literature reviewed probability failure on demand, we can see the jet fire event has nearly reduced by 100 events per year, and the flash fire events have somewhere reduced by 20 events per year. And both of these, if we try to put them again in the risk matrix, we can see now these are somewhere in the levels of conditionally acceptable or tolerable. So somewhere we have successfully tried to reduce the risks in this process, so that the feasibility of the project increases, and as well as we can have more and more inventory in such situations. Of course, these safety barriers are open to recommendations. There are few more barriers that we can implement, let's say a firewall, or we have thermally activated pressure relief devices that can be set in the picture to reduce these events much more. Next slide, please. So coming to the recommendation parts, as based upon the safety barriers we have, so we recommend that the hydrogen detection system we have should be of the capacity that even if there's a small leak, and let's say there's 1% volume percent of hydrogen that has accumulated in the air, the hydrogen detection system should activate an audible alarm and should trigger the automatic shutdown system. So that will immediately stop the supply to the entire station. This is particularly because we don't want hydrogen to reach the lower flammability limit in the air, so that we'll avoid any potential ignition scenario in this situation. Similarly, based upon this, the automatic shutdown system should successfully stop the electrical supply to the fueling components as well as to the system area. And the entire inventory of hydrogen should be stopped within the isolation wall limits, so that there's no further hydrogen. If there's a leak, there's no further contribution or increment to the accumulation of hydrogen in air. Then lastly, for the venting system, we have the National Fire Protection Association, NFPA2, has provided strict guidelines for what should be the design of such venting systems, what should be the distance from the dispenser to the canopy, what should be the ground level elevation from the bottom of the dispenser to the ground. All of these have been mentioned in detail by NFPA2, and along with the Compressed Gaseous Association G5.5 standard. Next slide, please. Additionally, we also look out at certain human errors that are very common or that have been noted previously in the conventional gasoline and diesel stations, is that there can be a potential chance that maybe you're refueling and you are unsuccessful in detaching the hose from the vehicle, and there's a sudden drive off which can damage the dispenser and can maybe result into catastrophic rupture. So in this case, a breakaway couple is suggested that will safeguard the dispenser. It should be attached at the dispenser fuel assembly line as well as the hydrogen unloading hose, and it should be in line with the requirements outlined in CSA ANSI standard, particularly the 4.4 hydrogen series that talks about different valves and different joints that should be used in this particular scenario, because we are dealing at higher pressures and temperatures going at minus 40 degrees Celsius. So the breakaway couple should be in line with that. And in the last, we talk about staff training and certification, because ultimately in emergency scenarios, the first person rescuers are going to be the people who are already present on site, who are either working at the retail station or are at the maintenance site for maintaining the equipments at the refilling station. So adequate training should be provided in terms of how these procedures are carried out, what are the properties of hydrogen, and what can be the consequences of a leak. So they should be briefed about the operational procedures at the refilling station, especially the hydrogen tube trailer staff that are going to do the unloading part, which is a crucial part. And ultimately, if there's a failure of any of the safety barriers, the study also recommends to have certain emergency push buttons that can be manually pushed by the staff that is present on site in order to stop the entire operation at the refilling station. Next slide, please. So to conclude, the frequency analysis, we tried to derive it for different leak sizes from 0.1% to 100%, and we saw that 1% and 10% leak sizes have a very small difference. So we chose 10%. We derived the separation distances for both the scenarios. As we can see, we have the highest one for the 700 bar from the dispenser area of near about to 39.1 meters. Now, all of these zones as highlighted should not have any ignition sources, let's say a mechanical or a faulty electrical equipment or a mechanical spark, because as Dr. Lianne in the very beginning mentioned about the highly ignition nature of hydrogen, which has a very minimal ignition energy of just 0.02 microjoules, that can easily ignite even if there's a small ignition source. So particular care should be taken that these distances do not have any ignition sources. And with the safety measures recommended in the study, we can considerably reduce the frequency of such events to near about 200 events for jet fire and 20 events for flash fire. Next slide, please. So any comments or questions regarding the risk assessment part?
So I'll read out some of the questions, just being conscious of time. We may not be able to get to all of them, but we have a question. How did the authors confirm the accuracy of the data? Any experimental or other modeling or other techniques for risk assessment?
Yeah, so that's a good question. So initially we looked at the work that has already been carried out by Sandia National Laboratory, because we do not have much of incident data for hydrogen because it is new in the fuel form right now. So there were certain Bayesian analysis conducted. So all of the frequency data and was integrated based upon the Bayesian analysis that was conducted previously. And that is the basis for the development of the HIRAM tool that we initially talked about, which was used in the assessment.
Great, thank you. Oh, sorry, was there anyone else who wanted to jump in on that? No? Great. So there's another question on, have you considered looking at having a multi-fuel station operating in Alberta?
Yeah, that's a good point actually, because that is something we need to look at briefly, because if we are getting three different fuels in proximity to each other, let's say we have gasoline, diesel, and hydrogen in the same station, then of course there's a potential that the radiation can reach to some other fuel, which is again combustible, and there's a possibility of domino effect. But yes, definitely that is what we are also trying to look up to in our future work.
Okay, and one more question. This attendee asked, a concern with hydrogen is its explosivity. Beyond fire, jet fire, flash fire, etc., are there any other plans to include explosion scenarios to this QRA study?
Yes. So in this case, as we look at the footprint of the particular station that we have chosen, it has a larger footprint, and we try to make sure that the model has minimum confined areas or confined zones. So the congestion limits are way below. So there's no chance of accumulation of hydrogen. So we completely eliminate the possibility of a vapor cloud explosion or any kind of explosion in this scenario. So that was the particular focus mentioned in the study.
Perfect. Thank you so much. I'll pass it over to, I believe, Dr. Lianne is presenting next.
I'll continue with the
Oh, sorry.
initial part, and then we have Dr. Lianne. So coming to the regulatory gap analysis part, so we particularly looked at the fire code. So the National Fire Code Alberta Edition 2019 regulates the fire safety in Alberta, and the code specifies technical requirements for building construction or demolition and fire protection. So there's a particular part that is included in this fire code that talks about the flammable and combustible liquids, and all the fuel dispensing stations in Alberta need to comply to this particular code. But this code does not currently explicitly mention requirements for hydrogen fueling. And certainly we need to talk about the separation distances based upon the technical requirements or the technicalities like the inventory of hydrogen or the pressure levels of hydrogen that are present. So this can be referenced to what the California has been already doing. They have been in the business for a long in the hydrogen refilling stations. So they set out the minimum separation requirements that hydrogen systems or hydrogen refilling stations should have. So that is what we try to recommend in this part. Next slide, please. So coming to the zoning laws. So based upon the land that we have identified for the potential refilling station, it falls under the Strathcona County municipality. And so there are certain bylaws aligned with these particular jurisdiction. And currently they do not address particularly what should be the distance requirements for establishing such special refilling stations in Edmonton. And so therefore, we highly recommend considering consequence and associated harm distances that we have particularly carried out in this situation based upon how much hydrogen we have, what kind of vehicles we are refilling, whether they are in the 350 bar scenario or in the 700 bar scenario, or both the scenarios. And we should evaluate appropriate distances. That should be a part of the recommendations for zoning laws as well. Next slide, please. So to have a brief understanding of the regulatory gap, we try to divide the codes and standards for the hydrogen refilling station specifically into 4 categories: the tube trailer delivery part, the components involved, that is the component design part. Then we have the operations, that is the refilling operations. And the 4th part is the safety standards that we already have in place. Next slide, please. Okay, so when we look at the tube trailer delivery part, so the standard given by the Canadian Standards Association, CSA, the B339 2018 edition particularly talks about the selection of cylinders, spheres, and tubes that should be used in the transportation of dangerous goods, TDG. And so this particular standards needs to emphasize more on the filling pressure limits for hydrogen containers in this. So that should establish what should be the threshold for pressures while we are filling the tube trailers, which is again something that we can look up to from the Californian code, specifically the 49 CFR 173 that we have recommended to look at, to how they have categorized these particular threshold levels. Next slide, please. Coming to the component design part, so there's one established standard known as the Canadian Hydrogen Installation Code, which has been established by the Quebec Board. And this particular standard talks about the separation distances, but does not provide guidelines for classifying those hazardous zones and determining risk-informed separation distance, especially for electrical equipments, because apart from the gaseous part, we have certain electrical equipments in place that we need to thoroughly look at, because we need to establish certain boundaries from such equipments which are highly sensitive. So that we recommend a detailed quantitative analysis. Also, recommendations from the Canadian Electrical Code Part 1 can be looked upon to bridge this following gap. Next slide, please. And ultimately, for the refilling of operations, we recommend these standards, which are initially the binational standards, that is the Canadian and the American standards that have already been published in the hydrogen series, that talk about the dispensing systems as well as what kind of material should be used, what kind of safety system should be used. Then followed by the international standards and the Society of Automotive Engineers standards that are currently being used in the established stations, even in Canada, especially in British Columbia, and I guess Ottawa also has a refilling station. So these are the standards currently being applied. Next slide, please. So coming to the safety standards part, we have the NFPA 2 that highly talks about what are the safety aspects we need to look at. Then we have NFPA 1 that talks about the fire specifications in such scenarios. Then we have the ISO standard that talks about the gaseous hydrogen refilling station, provides us with what kind of valves and what kind of joints should be used in this situation. And finally, we have the fire code that we have addressed that we need to explicitly talk about hydrogen refilling stations by addressing the risk assessment which has been carried out in this particular study. Next slide, please. So to conclude with, most of the codes and standards that we scanned, particularly for refilling stations and have been currently being used, are lead up to the design and operation requirements of refilling stations, but particularly looking at the zoning laws, the provincial fire code, and also the Canadian hydrogen installation code that potentially can be a guideline for all of the refilling stations that will be built henceforth in Alberta. So these are the particular recommendations we look up to that we need to talk about the risk zones and the guidelines for classifying those zones, and also having certain specific regulations for hydrogen, specifically in fire code, zoning laws, and the Canadian standard that we talked about. So any comments or questions on this particular part?
So we have a question. Does the Canadian Hydrogen Installation Code talk about separation distance? Is that good to begin with?
Yeah, actually, so the Canadian Hydrogen Installation Code has an appendix designated particularly for the separation distances that talks about based upon how much inventory of hydrogen we have. But that is just one particular part of it. We also need to look at what pressures are we dealing with, what pipe sizes we are dealing with, as we have briefly described in the study, and probably that can somehow take it to another level, talking about, because we are talking about the technical part of hydrogen, not just based upon how much hydrogen we have on site. But yes, to answer your question, it addresses the separation distance.
Great. And one more question we have, maybe this participant can expand if there needs to be clarification, but they asked, what is the heat flux of the fire?
So the heat flux is generated at different levels, and that is what we described through distances. The distances showed were for 4.7 kilowatt per meter square, which was the set criteria. And as we go about to 25 kilowatt per meter square, of course, the distances decreases. But that wasn't our point of concern at that point. We looked at the criteria that we set.
Perfect. Thank you.
So I request Dr. Lianne to proceed with the next part.
Yeah, thank you. Yeah, great questions. I see there's other questions in the Q&A, and we'd be happy to answer those afterwards. Some of them are a bit redundant, and some we end up covering, as Anirudha mentioned, with regards to the regulatory gap analysis, but we'd be pleased to share our interim report. We also have a paper on this that is about to be some minor revisions, about to be accepted in the International Journal for Hydrogen Energy. So we can share that with you as well. So that will probably answer some other questions of yours. So I'm just going to conclude here super quick, so we can leave some more time for questions to talk about kind of the next steps. As I mentioned at the beginning, this is a multi-phase 2-year research project funded by Alberta Innovates. So after the hydrogen refueling station, we're also now looking at the next step is to look at hydrogen delivery and distribution from the production plants to the end use. And we're looking specifically at delivery via pressurized cylinders or tubes, so carried by a tube trailer. Number 2, delivered via cryogenic tankers, so it's a liquid delivery carried by a tank truck. And 3rd, delivery via distribution pipelines, so hydrogen and natural gas blend in most cases. Next slide, please. So our methodology, and this parallels what we did for the hydrogen refueling station. So it really is looking at then quantitative risk assessment methodology. On the left is for delivery distribution, specifically tube trucks, and on the right, it also includes load distribution pipelines. So it's really thinking about loading locations, travel routes, unloading locations on the right-hand side or left-hand side, sorry, point of distribution, end of use site, and then process modeling, hazard identification, consequence, frequency analysis. Again, looking at individual societal risk and then risk mitigation strategies. So very parallel to what Anirudha has discussed with regards to hydrogen refueling stations. The same procedure entirely, but looking at transportation and the routing of that. Next slide, please, Vanessa. So again, our location of the central distribution terminal. It is Lindy's Tube Filling Facility in Fort Saskatchewan on 119th Street. And this location will be considered for risk assessment for the unloading scenario of the hydrogen into trucks for delivery. Next slide, please. Really, we're then looking at the transportation utility corridor to a blending station into the distribution network, and the total network area is 1.13 kilometers squared. Next slide. And as part of this too, and it's a part of the broader questions that have been asked by attendees, is really how do we start to understand what are the authorities having jurisdiction for this? And this is it's not the best figure for these slides. Sorry, it's not advice I would give to my students ever, and yet I've broken it myself. But we'll be happy to share the full report with you, and it's a better graphic. But you can see here, just in terms of the hydrogen project, in blue is we've got the Alberta Energy Regulator on the left-hand side and the Safety Codes Council. In red, we have various municipal affairs and the Canadian Energy Regulator. And then in blue, we've got kind of public notification processes. So it really does describe, sorry, in green, describe all the authorities having jurisdiction for the design, the operation, and then emergency response. Next slide, please. So that's it in terms of our overarching project, the motivation for it, our approach towards it, using our first milestone report with regards to hydrogen refueling stations. And the next step is looking at hydrogen distribution. So we've got 8 minutes left. So if you have any other questions for folks, I see there's some more in the chat. Again, we'd be happy to share our full report with you and then our article. Dr. Adnan Khan is also present. If you have any questions with regards to development of the value chain and life cycle assessment more broadly, he can answer kind of the broader, the technical and commercial questions about what that looks like in Alberta. So we're pleased to take your questions. Please put them in the chat.
Great. I think we probably have time to address them right now. We have 5 questions. So from the earlier presentation, we have a question on the weight percentage of P1 to P3. If you need any clarification, maybe the person who posed this question can expand.
Yeah, so P1 to P3, of course, the weight percentages are not same because the contribution of each leak, let's say if you have a leak from cylinder, the frequency of leak occurring from that cylinder is different. So similarly, a leak occurring from a particular valve is different. So ultimately, all of these individual components lead to different values. So P1, P1.1, P1.2 lead to some different values. So therefore, P1, P2, P3 won't be categorized in the same weight percent category. Of course, their contribution is going to differ.
Great, thank you. We have a question on how leak sizes were generated. Do we have the same leak size considered throughout the station?
Okay, so leak sizes were generated based upon the pipe flow area associated to each section, as we have divided the filling station into 3 different areas. And that was derived based upon an open source tool, which is known as HYRAM, that has been particularly developed for hydrogen. So based upon the pressure conditions, the ambient conditions, and the inventory of hydrogen, and particularly the pipe flow area, these leak sizes have been generated using that particular tool. As I said, the Bayesian analysis is the background framework that works to generate these leak sizes.
Great, thank you. And we have a question on replacing tube trailers with continuously operated pipelines to HRS. Is this a good solution? Seeing that pipelines are much safer and have 0 carbon discharge required for transporting challenges.
I mean, yeah, ideally we have a lot more other solutions as well, rather than just operating pipelines. Because if you're talking about distribution pipelines, then the pressures would be very less, like near about to 700 kilopascals, and then we'll be needing much heavy compressors to, use them again. And again, we need pure hydrogen in this scenario. And if we are using hydrogen through pipelines, currently we are looking at blends of hydrogen, which is the current scenario, looking at the costs of hydrogen we have and looking at the feasibility of projects. So yes, ultimately that can be, or that will be the solution of delivering hydrogen, because that is the best possible way to deliver. But currently, no, tube trailer is the one that everyone would prefer right now.
I can just add to what Anirudha was saying here. When you're trying to build out hydrogen supply chains, it is very important to remember that hydrogen supply chains or value chains do not exist today, right? And what we're trying to set out to do, it's really a matter of supply and demand. When talking about hydrogen pipelines specifically, we're doing a lot of work in terms of techno-economic analysis of different ways of delivering hydrogen. And hydrogen pipelines are absolutely the cheapest way when you get the right demand to really deliver hydrogen. But right now in early stages, the best way, or probably the easiest way, is via tube trailers or liquid hydrogen delivery. And that's what Anirudha was presenting. So just another aspect to the way to think about the entire value chain.
I see we have a question from the audience. I believe you can speak if you'd like to, Muslim Fatahi.
Thank you for your presentation. My question is about the distance. The distance you obtained, the highest one is near 40 meters, yeah? The highest. In the literature, for the pipelines, we have more than 70 meters. You have a different
Yes. So
differences with the literature, mostly because your method of the quantitative risk assessment based on the algebraic equations, that it's estimation, not, for example, from the CFD modeling. I mean by CFD, computational fluid dynamics, not code fire and something like that. Yeah.
Okay. Yeah, I get your question. So yeah, for pipeline particularly, so this harm distances are based upon how much inventory you have, how much pressures we are looking at, and what leak sizes we are particularly looking at. Now, if we go with higher leak sizes, let's say 100%, or if we look at catastrophic failure scenarios, which is generally the case observed for pipelines, of course, the distances are going to go beyond 40 meters. But looking at the probability or likelihood of occurrence of such leaks, we tend to somewhere rationalize as to which leak has the highest probability of occurrence, and we look at that and we look at those distances. But of course, if we have higher leak size consideration, the distances can go beyond 70 meters, as you rightly said.
Great, thank you. We had one last question for Dr. Lefsrud's presentation, I believe. So they posed the question, on the right hand of the bow tie, there were protections involving gas detection. Any thoughts on adding flame detection? If so, what kind of technology specific for hydrogen?
Actually, I will, I'll move that to Anirudha, that question.
Yeah, so in the bow ties, yes, definitely we can look at flame detection, and we can look at particularly at infrared and UV imaging detectors that can, detect that ignition. But somewhere we went to the very pre-primary basis of looking at the leak, because that is where post which we can look at ignition. So definitely we can put in recommendation certain catalytic sensors or maybe ultraviolet sensors to detect flames early on, but we look at the gas detection primarily.
Perfect. Thank you so much, everyone. I believe that is the end of our time today together. So I wanted to thank everyone for presenting their research today and taking the time to speak with us. And thank you to everyone who has attended and posed their questions. And I just wanted to mention that a recording of this webinar will be available on the CIAC website shortly. So thank you so much for attending today.
Yes. Thank you. Thank you so much.
Thank you, everyone. Thank you.